like to tell you about today is a idea for how one might actually accelerate the search for new materials by targeting in on their functionality. This is work that Gabi and I have done together in the past. Let me just begin by by giving you some numbers, which would be if your intention, for instance, would be to to discover a new superconductor. The numbers are really strongly against you. In particular, this is a picture of what's called the materials development pyramid. It's an idea that was put forward by Bob Kava. And so the first thing is that, of course, you want to consider real materials. And in the International Crystal Structure Database, there are about 350,000 unique inorganic compounds that you have to choose from. So that's not very helpful. And so presumably, you would also want to be guided by perhaps materials of interest, which would be the subset of all materials that would be superconductors. Maybe there are 2,000 such materials. But even if you have a new superconductor, it may not have the properties that would be useful, in fact, for your applications. The right critical field, the right critical current, the right TC, not toxic, made of inexpensive materials, it needs to be ductile, these sorts of considerations. And even if you are on top of that, at present, there are fewer than 10 superconductors that are actually being used in current applications for real technologies and for real societal benefit. And so you can see that this is why it may take a generation for a new material actually to be used in real technologies. And our ambition is to try to speed this process up. Certainly electronic structure calculation, everything good, Emmanuel?
Yep.
Good.
Yes.
So certainly electronic structure calculations with their increasing realism could be a part of such a scheme. And in the project that I'm going to tell you about today, our motivation initially was to predict new superconductors. But the problem that we have to confront with those calculations is that we have no theory that would predict from them the conditions for superconductivity in some specific terms. The electronic structure calculations, however realistic they are, also would need to develop some sort of Cooper pair susceptibility, some sort of a marker that would allow us to identify potential superconductors. And so in view of those two observations, we are at the phase of employing a phenomenological approach, where we know that superconductivity can be an option when other forms of order would be suppressed. And so we'll be looking for those sorts of things in the electronic structure calculations, such as the suppression of a charge gap at a magnetic moment. So the scheme that we potentially have in mind has two steps. And the first is what we call the validation phase. And the proposition here is that electronic structure calculations could accurately determine the properties of known compounds using only the crystal structure information as the input. And that this scheme should in fact be pertinent even when correlations are strong. So that's the proposition. What we would provide experimentally would be a known crystal structure. Then we would do the best electronic structure calculations possible, and we would use them to predict the basic properties of the system, which might be the electronic gap, size of a magnetic moment, and importantly, spectroscopic measurements like the optical conductivity or the susceptibility. And by comparing those calculations to experiment, we'll get a good idea about what the relevant parameters are for the theory, and that will give us confidence to apply it to similar sorts of materials. So that would be the scheme. All right, so we tested this idea by looking at a particular family of compounds. So I think we're familiar with the iron nictide and iron chalcogen compounds. And they have cousins, if you like, that form in the same sorts of structures, but using manganese instead of iron. And so the plot that I'm showing you here is an organizational scheme where we went to the International Crystal Structure Database, and we just collected all the manganese-based compounds that formed in the same structure types as for the iron pnictides. And I've rank ordered them here in order of the moment per manganese ion. So there are two kinds of manganese square net compounds, and you can see on the left that the manganese moment can approach 5 Bohr magnetons per manganese, and in this regime you have magnetically ordered insulators. Alternatively, if you look on the right-hand side of the diagram, you can see that there are compounds where the moment is only a few Bohr magnetons per manganese, and these compounds are typically correlated metals. So for the purpose of this work, we focused in on a particular compound, which is that yellow box. This is lanthanum manganese phosphorus oxygen. It forms in the same structure as lanthanum iron arsenic oxygen. And this material is known to be an antiferromagnetic insulator, has a gap of about 1 volt. The experimental gap is about 1 volt, and 3.2 Bohr magnetons per manganese. And so it is conveniently located between the transition from antiferromagnetic insulator to an antiferromagnetic metal. So the first step of the handshake, or the validation phase, is then to determine if we could understand the origin of the gap in this material. So there are 4 panels that are shown at the right that develop our argument. And the top one would be the results from DFT. And you can see that at the Fermi energy, there is no gap. And so if DFT predicts that this is metallic, while the experiment says that there is a gap, we can construe that this compound is a correlation gap insulator. The second panel down takes the DFT and adds a quite large Coulomb interaction of 10 volts. And you can see that that did not materially change the situation. Again, there's no gap. And so that suggests to us that this material is not a simple Mott system. The first indication of a gap happens when we add a Hund's interaction of about 0.9 volts, and there is no magnetic order present in this state. And you can see that for the first time we see a small gap. And finally, we can get a realistic size gap by adding in a Heisenberg interaction, suggesting that the gap is enhanced in the antiferromagnetic state. So this is the first step of the validation phase, which is we can understand the origin of the gap and we can predict it with reasonable parameters to match up with the experimental value. So the next thing that we did is that we looked at a spectroscopic property, and that's going to be the optical conductivity. And these are experiments that were carried out by Dmitry Basov's group. The measurements were carried out as a function of pressure that we would hope would suppress both the magnetic order as well as the gap in this material. So if you look at these data, what I have plotted here at the top are the experimental results. This is actually not the optical conductivity, but its inverse. And the black curve on the right is at low pressure. And you can see that as you increase the pressure and go towards the left, I wonder if you can you see my little arrow?
Yes.
All right. And so this is increasing the pressure, and you see that the gap, which is where this line intersects the axis, it's about 1 volt at low pressure. And it moves to lower values as we increase the pressure. And somewhere between the cyan data, which is 19 GPa, and the pink data, which is 22 GPa, you can see that the gap disappears. So if you look down here at the lower right, the black and the red data are in fact values, the measured values of the gap. And the green data would be the calculated value of the gap. And you can see that they vanish over here somewhere near 20 GPa. Interestingly, the blue data show the resistivity at some fixed low temperature, and you can see that it also drops in parallel with the size of the gap, and eventually it saturates out here at high pressure, also confirming the idea that the gap collapses. Here are these would be the electronic structure calculations below and above the gap. And the pressure where the gap disappears, and you can see that is faithfully reproduced in these calculations. Finally, these are DMFT calculations of the same thing as was measured experimentally. The colors are the same top and bottom for the different pressures, and you can see that the gap marches down consistently as a function of pressure and disappears somewhere between this pink and green values. The green value is 16 GPa, so that's pretty close to the critical pressure. So from this perspective, we feel like the calculations can actually reproduce in some detail the experimental properties of these materials. So encouraged by this, we can go on to the next phase, which we call the discovery phase. And so essentially, this, for an experimentalist, the purpose here would be, in fact, to try to provide as many different crystal structures and their parameters as would be possible, so that the calculations can guide through them and then provide the same sorts of information as we had for the lanthanum manganese phosphorus oxide to guide the approach to the desired functionality, perhaps superconductivity. And the idea then would be that if the calculations are more straightforward than actually growing the materials themselves, that is, that they would take less time, then this would be a viable route for making decisions about which materials you'd like to focus on, even without making those materials at all. And this would allow us then to reserve the considerable effort that's required to grow large crystals for the most promising compounds and really dig in to carry out the physical characterization, but only when the system seems sufficiently promising. So that would be the scheme. So the reason that it might potentially be advantageous is, of course, that to do synthesis is really quite time-consuming, and in order to be successful in the synthesis world, you also have to be very lucky. At least traditionally, that's been the situation, and I suppose that part will never change. And so here are some pictures of my colleagues who are doing various steps, just to argue to you that there's a lot of physical work that's involved. It's a very tedious and long step, and you could live with that, except that essentially, there's a real opportunity cost that's involved with making a decision to pursue a particular class of materials. It could take months to produce crystals of a new system that are large enough for physical measurements. Essentially, you can't decide whether a material is promising until you've done a pretty serious job of the physical characterization. And it takes exactly as much time to reach the decision point for both promising and unpromising materials. And so, that is not the greatest. The scheme that I want to tell you about next is an approach that we developed in our group where we hope to actually get through the synthesis phase a lot faster. And the way that we propose to do that is that instead of going through all the steps that are shown in these pictures at the top of the page, instead what we're going to do is we're going to take our growths to the synchrotron, and we're going to grow the materials in the synchrotron beam and study the diffraction patterns in real time. And this will give us some information about how the synthesis proceeds, the sequence of chemical reactions. And I'll show you some examples where what we can do in an afternoon at the synchrotron would take months in our laboratory. So here's a picture of the experimental setup. Essentially, we have these alumina crucibles where the reactions are going to take place. Because X-rays have to penetrate the alumina, we need to use high energy X-rays above 10 kilovolts. And this is a picture of the XPD beamline at the NSLS2 synchrotron. The X-rays come from the right. They're indicated by this red line. The sample is placed here at the scattering center, and the diffraction pattern is collected over here on this 2D detector. The sample is going to be warmed by this focused lamp, and that we can control the temperature carefully. And essentially what we're going to do is we're just going to study the diffraction pattern as a function of time as we increase the temperature of the sample. And here is our intrepid team from the NSLS2 on the right who carried out these experiments. So I'm going to start off just by giving you just a simple example of why this works so well for us. And so at a certain time, we had the idea that we might want to grow this material, calcium-3, phosphorus-2. It was an interesting 3D Dirac semi-metal. And at the time, the samples were being grown in essentially a solid-state synthesis approach by just putting the right amount of calcium and phosphorus into a tantalum tube, heating it, and then cooling it down. And the problem with that is that the crystals were very small, so that made the experiments super difficult, and many products were produced in the tube, meaning that the synthesis wasn't particularly efficient. And so our idea was that we would try to grow this from flux instead of by solid state reaction, because this is a good route to make large single crystals. The idea from flux is that you would dissolve the calcium and the phosphorus into some low melting point compound, maybe a metal, maybe a salt, raise the temperature to get a homogeneous melt, and then slowly lower it so that the crystals would drop out of solution. Exactly like growing sugar crystals from a saturated solution of sugar and water. So the first thing we have to do, though, is find the right flux. And so here's a picture of a diffraction pattern. So this is a function of angle. So these are each diffraction peaks. And this is as a function of time. And on the right side, you can see the temperatures that were present at each of those times. So these red lines here are the flux, which in this case is potassium chloride. And these are diffraction peaks from a powder of calcium phosphorus that we made. So you can see that as you raise the temperature, the diffraction peaks are there, and then at a certain point they disappear, just like around 750 degrees or 800 degrees. And that means that the potassium chloride melted. There are no more diffraction peaks. You can see that we have only weak diffraction peaks from the calcium phosphide in this region. And so we would construe then that the calcium and phosphorus dissolved into the flux. And if we then if we would cool down again, you can see that those peaks intensify and the flux peaks come back. This means that the flux solidified. So we would say this is very promising as a flux. In contrast, if we consider sodium chloride, this turns out not to be any good. These again are the flux peaks, these red ones. And as we go into the melt here, you see that what we started with, which was calcium 3 phosphorus 2, actually turns into a new compound, calcium phosphide. So that showed us right away that sodium chloride flux would never work. It would yield the wrong compound. So that's just a quick example. We tried a bunch of other things, indium flux, bismuth, tin. They were all shown to be no good for one reason or another. So that's sort of a simple application how this could be useful to us, presumably mostly useful to us if we had a synchrotron here at UBC, which we don't. And so what I'd next like to show you about would be an experiment which would test a theoretical proposal. So this proposal comes from a paper by Chucky and Gabi Kotliar, and they made the proposal that if you took lanthanum cuprate and you replace the apical oxygens with one or more sulfurs, and that is shown over here. This is the These are the apical oxygens, and there are two compounds that would be formed if you had one or two of those oxygens replaced with sulfur. And this presumably would reduce the charge transfer energy, and that would lead to an enhancement in TC. So a interesting thing about this paper was that it actually predicted certain synthesis pathways that we could follow. And so in fact, we took that challenge and tried to synthesize the lanthanum cuprate with sulfur on one or two apical oxygens. So as a warm-up for that, I'm showing you here the data that tell you how lanthanum cuprate forms. And so in this, so again, these are the diffraction peaks that I showed you before, and these are the temperatures at which the peaks were observed. And so for us, the starting material would be lanthanum oxide, lanthanum 2 oxygen 3 plus copper oxide. And so here's a fun fact. Even if you have lanthanum oxide in a bottle in your chemical shelf, it is not lanthanum, it is not that material. You can see that our solution of these diffraction peaks actually is that it's another compound. It's absorbed water and it has become this compound instead. So, well, life is tough. As we raise the temperature, you can see that around 400 degrees, your compounds, the compound degrades into something else, which is this. So it blows off some water and it reduces to this. And then finally, above 600 degrees or so, you actually form what you wanted, which was lanthanum 2 oxygen 3. So what we can, so what's shown over here at the right-hand panel is the starting materials, which is the copper oxide in blue, and then that lanthanum oxygen hydrogen compound in black. You can see that that is suppressed at 400. The other lanthanum oxygen hydrogen becomes available. That is displaced in turn. And the lanthanum 2 oxygen 3 is present in the stoichiometric quantities above, say, 600 degrees. So now we're ready to go. We have lanthanum 2 oxygen 3, and we have copper oxide. And only above 900 degrees do you see green, which is the lanthanum 2 copper 04, which grows spontaneously from that mixture. So that's how lanthanum cuprate forms. It has a multiple step reaction. So now I'll show you what happens when we try to introduce sulfur. So in this case, we started with the proposed synthesis path, which is this compound, lanthanum 2 oxygen 2 sulfur, which is a reagent, plus copper oxide to form this compound, which is lanthanum cuprate with one less oxygen replaced by sulfur. So in this case, what you see is that the diffraction peaks are essentially unchanged up to about 760 or so. Here is the copper oxide. Here's the lanthanum oxygen sulfur ternary, and you can see that they are present and only become reduced once you get above 700 degrees or so. And here you see the formation of two new phases, the red and the blue phases. Red is copper 2 oxygen. The cyan color is a lanthanum oxygen sulfur compound. And so that's the first step of the reaction, which is shown here, where the copper oxide is reduced to copper 2 oxygen, and that would have oxygen 2 minus, and so then copper must be 1 plus, not 2 plus, which is really a pity. The second stage of the reaction happens at something like 1,000 degrees, 1,100 degrees, and that's the copper 2 oxygen breaks down, forms with this compound to make the end product, which is lanthanum copper sulfur oxygen plus excess lanthanum oxide. So this didn't go exactly the way we had hoped. The total effective reaction is shown here, which gives you an idea of what the yields are in the reaction. And so essentially we form this quaternary compound instead of the quaternary compound we were after. And the downside of that is also that this is a copper 1 plus system, not a copper 2 plus system. So presumably not that interesting. All right, something similar happens when we take another route, which is lanthanum oxide plus copper sulfide. This is another synthesis pathway that we could consider. And the upshot is that, again, we have copper sulfide, and that is reduced to copper 2 sulfide in the first step. And then the final product in this case is a cleaner synthesis of lanthanum copper sulfur oxygen. So again, that didn't work out. But I want to stress that we found all that out over the course of maybe a day or so at the synchrotron, as opposed to spending months trying to make that work. So of course, at this point, one is a little discouraged and wonders if you can, if it's possible to make touch again with the basic idea, which is that the electronic structure calculations could give us some guidance. And for that, we turned to the materials project as a source of DFT calculations. And so in this next step of this talk, I'm just going to go through those syntheses and show you how the total energy that's associated with each one of the reactions actually develops. So here again is the synthesis of lanthanum cuprate, and this is the reaction. Lanthanum oxide plus copper oxygen gives us lanthanum cuprate. And so what we found from the total energy calculations would be that this reaction is thermodynamically not favored, meaning that you'd have to provide 48 millivolts per atom to go from the reactants to the product, 48 millivolts per atom. So of course, I have to point out to you that lanthanum cuprate does exist. It forms by this reaction. And so the interpretation that we would have would be that possibly thermodynamics is not the only thing at play here. Kinetics could also stabilize this reaction. That's always a possibility. Or it could also be that this is a correlated material, and so DFT is not going to be sufficiently accurate even to give you an idea of the synthesis pathway for the formation of the compound. So at this point, I say we wouldn't know how to answer that question, and effectively what that would tell us is that we'd be up for trying anything that was within 50 millivolts per atom of being stable, if that makes sense to you. So if we look at this other reaction where we started with lanthanum 2, oxygen 2, sulfur, and is there a question?
5 minutes, Meigan.
Okay. Yeah, so I'm not gonna make it, but essentially what we find is that this step between copper oxide and the reduced version of copper, which is copper 2 oxygen, this has a negative energy of 222 millivolts per atom, which tells us that reaction is very stable. And in fact, it is, oops, sorry about that. It is, in fact, it dominates the total energy balance for this reaction. And so I think that fundamentally the reason why it's impossible to put sulfur into copper oxide is this redox principle, which I think any chemist would have told you. So here is the conclusion of that experiment, which would just tell us that the basic problem is that redox reaction happens basically at all sulfur concentrations at a relatively low temperature, let's say at 600 degrees. And so that means that the copper is already reduced at low temperature. And since the lanthanum cuprate forms at high temperature, that's why this whole scheme falls apart. And it's, in our view, impossible using these sorts of techniques to introduce sulfur into lanthanum cuprate, although there may be some soft chemistry approaches that you could get around, which would mean that the reduction wouldn't happen by the time the cuprate had formed. So given that I'm out of time, I will just briefly tell you that Gabi and Chuck also looked at the convex hull of this quaternary system. There are 31 known elements and compounds that are involved, And essentially, what we find from this comparison is that, say by magic, we had been able to make this material where there were 2 apical oxygens replaced with sulfur. These calculations indicate that compound would break down into these 2 products and release an energy of 469 millivolts per atom. Okay, that is a lot of energy. And so essentially what that tells you is that this is incredibly unstable as a compound, and that it would instantly break down into these products. And so I would say that it would be advantageous for theorists to also think about working in this field of understanding solid-state reactions, because I can tell you that chemists and materials-inspired physicists such as myself know very little about these solid-state reactions. And so this would also be an enabling step for being able to hone in on successful materials as quickly as is possible. So with that, I just want to line things up for the next speaker to tell you about a separate project that we did. And so you might have construed from the cuprate work that sulfur and oxygen should never be found together, but we were not discouraged by that. Instead, we decided to look at cobalt-bearing compounds to see if we could find some new superconductors there. And one of the compounds that we looked at is this barium cobalt sulfur oxygen compound. And in fact, it does turn out that this material is stable and can form from a melt. And we presume we could grow large crystals from a flux if needed. And so that is, I can't go into the details because of the time issues, but in this particular case, we were able to use our in situ experiments basically to explore the entire phase diagram from this side, where you have just barium, sulfur, and cobalt. This is barium cobalt sulfur 2, which is a known Mott antiferromagnetic insulator with a large gap and nail temperature slightly above room temperature. And you can see that as you start to mix barium oxide in for the barium sulfide for a large range of compositions, instead, our experiments show that you get this barium cobalt sulfur oxygen phase, as well as 2 other ternary phases. And when you are approaching the absence of sulfur down at this end, the barium cobalt sulfur oxygen phase, which is shown here, is what is stabilized. At the time, this material had not yet been reported. It is a new antiferromagnetic insulator. It has staggered planes of cobalt and lower nail temperature and a very small gap. And it's for this reason that we would be potentially interested in it for applications. So given that my time is now up, and I know that the next speaker will talk some more about this particular material, I'd just like to end by showing you our wonderful team. You can definitely tell the experimentalists because they get to wear the PPE and the theorists don't. Anyway, these are the people who really showed that this procedure would work well. And with that, I'd like to cede my time and ask if you have any questions.